Hey everyone, so I'm going to go on quarks and leptons. Actually, that's just the name of the chapter, but today I'm going to be telling you about some other particles and antiparticles and what they can decay. So, first of all, I need to tell you about cosmic rays. So, cosmic rays are high energy particles that travel from the stars through space, and most of them are fast moving protons, or they have like a tiny nucleus, okay, or small nuclei, because we are talking in plural, okay? So, when a cosmic ray enters the Earth's atmosphere, they create short-lived particles and antiparticles. So every time a particle is created, the antiparticle is created as well. Remember that antiparticles have the same rest mass, but they have opposite charges, okay? And they also create photons, okay? Now, from the particles that were discovered later on, and that are made by these cosmic rays, or particles that you can even get to be made in the lab, we have muons, pions, and kaons, and I'm going to tell you about all of them now. So, first of all, I put all of these in order of rest mass, okay? So rest mass, the arrow is going down, so it means that the rest mass increases as we go down here, the three different boxes. So muon has the lowest rest mass, and then is the pion, and then is the kaon. So the muon is also known as the heavy electron, and that's the symbol there, okay? The mu, sorry. So it is negative, heavy electron, so it has the same charge as the negative. As the electron, so it's negative. It has a rest mass that is over 200 times the rest mass of the electron, okay? Still, from all of these, is the one that has the smallest rest mass, okay? Then we have the pion. So pion has a rest mass in between the muon and the kaon. So the pion can also be known or called the pi meson, and can be positive, pi plus, negative, pi, this should be a pi, pi minus, or neutral, and again this should be a pi, so pi 0. It has a rest mass that is greater than the muon, which is the heavy electron, but is smaller than the proton, okay? And finally we have here the kaon. So the kaon is also known as the K meson, can have again a positive charge, K plus, negative charge, K minus, or a neutral charge, K0. It has a rest mass that is greater than the pion and is greater than the muon, but is smaller than the proton, okay? So all of these still have a rest mass that is smaller than the proton. Smallest rest mass of all is the muon, heavy electron, so negative. The other two, they have a higher rest mass, but because they are not heavy electrons, they can have any type of charge, so positive, negative, or neutral. And as I told you before, rest masses increase as we go down in this slide. So muon, smaller, then pion, or pi meson, and then kaon, or K meson. Alright, so this is an example, is an actual photograph taken at CERN, so from, in this case, the decay of the pi meson, okay? So this is how they can see, so they can look at the trajectories of the particles, and then they can take conclusions, several conclusions to do with properties, charges, velocities, okay? So, about these particles, they tend to be the result of the strong nuclear force interaction. So it's good that we know that, because sometimes we need to say what type of interaction they have. So this one, strong nuclear force. Later on you will get to know a little bit more on how you figure out if strong or not the strong nuclear force, okay? They can also be created using accelerators, I'll go there later on, in which protons collide head-on with other protons at high speeds. The kinetic energy of the protons is converted into mass in the creation of these particles. So as you know, you can have you can get some particles that when they combine they can create new particles, when they collide they can create new particles. So that's here what we have, and then this allows the particles to be studied under controlled conditions. This is part of being studied and created in the laboratories. Their rest masses, their charges, and lifetimes were measured, and the antiparticles were detected as well, okay? Remember that for every particle there is an antiparticle with equal but opposite charge, and with the same rest mass. Now, these particles can decay. Now, you're going to find this a little bit weird maybe at first when you first hear it, but just think about it. First thing that you need to remember is that any particle that decays is going to create particles that are smaller, okay? So the kaon is the heaviest one of all the other ones that we saw, and it was heavier than the pion and the muons. So the kaon can decay into pions, it can decay into muons and antineutrinos, and they can decay into antimuons and neutrinos. So pions, and then if it decays into a muon, must decay as well on, as an antineutrino. If it decays as an antimuon, it must have a neutrino there as well, okay? Then the second one with the highest rest mass was the pions, or the pi meson. So charged pions, so the ones that have a charge, they decay into muons and antineutrinos. Same thing as before. Every time you get a muon, you must have an antineutrino or an antimuon and neutrinos, okay? So if you know the first one, you can kind of get the other ones, all right? So kaon decays into pions. Okay, charged pions decays the same as the kaons, but not into themselves because they are already pions. Now, if I have an uncharged pion though, it will decay into a high energy photon, all right? So memorize that. And then finally, muons. So they cannot decay into pions or kaons because muons are the ones with the lowest rest mass. So muons and antimuons, they are going to decay into electrons and antineutrinos together, or positrons and neutrinos together. So just look at the relationship. So muon is a heavy electron, right? So if it is going to decay into something smaller, it's going to be the electron or then the antiparticle of the electron, which is the positron. Now, in the kaons and the charged pions, if I would have muons and antineutrinos together, so negative charge and then antineutrinos, if my muons decay, I'm going to have electrons, negative charge, and antineutrinos. Let's look again in the top. Then I could have antimuons and neutrinos. So my, in this case, the muons would fall and then decay, and if I would get electrons, it would be antineutrinos, right? So positrons, it would be the neutrinos. Remember, antimuon here, positron here, which is the antiparticle of the electron. So again, I mean, this sounded weird the first time we saw, but then if you think about it, it's not that hard to memorize and to understand what can decay in what, okay? All the decays that we are talking about are going to obey the conservation rules of energy, momentum, and charge. And later on, we are going to talk more about rules of decays. Now, I told you that these can be created in accelerators and they can be studied in the accelerators. So I'm going to tell you about 3 accelerators we have. As you can see already, one of these is not really there to study these particles, but the TV tube is an accelerator. We have the Stanford Linear Accelerator in California, and we have the Large Hadron Collider in the CERN in Geneva, okay? So the first one, the TV tube, it accelerates electrons inside a tube through a potential difference of about 5,000 volts. The electrons form a beam that hits the inside of the TV screen, and then the magnetic fields produced by the electromagnets deflect the beam, so it scans the screen to create an image, okay? So, believe it or not, is an accelerator. Here we have. Now, the second one, so the Stanford Linear Accelerator in California, and that's how it looks like. So, it's the longest accelerator in the world. Accelerates electrons over a distance of 3 kilometers through a potential difference of 5,000 million volts. Compare it with the TV, which was 5,000. And then the accelerator can give us an energy, okay? So the energy of the electron accelerated through this PD, so potential difference, is 50 giga electron volts. Giga is 10 to the power of 9, okay? So 50 and then 9 zeros electron volts. Finally, probably the most famous accelerator, at least at the moment, is the Large Hadron Collider, as I said, at CERN in Geneva. So it is the biggest one in the world. Remember the other one I said it was the longest, something around the longest, and this is the biggest one. Okay, so let's not confuse or not, judge me straight away. And then the charged particles are accelerated to energies of more than, and now let's look at these numbers again, 7,000 giga electron volts. Again, let's not even think about the TV now. Now let's compare this one with the one that we just spoke about, the 50 giga electron volts for the one in California. This accelerator is underground, and this is the underground. Okay, so this is just a picture showing where it would be underground on a 27 kilometer circumference ring. That's the main ring. There is another one in here, and there are several in here as well, okay, because we need to accelerate the particles in different stages. Now, for comparison, the room temperature, the thermal energy of a molecule is 0.04 electron volts, okay? And you already know this, but the electron volt is the energy given to an electron by accelerating it through a potential of, or a potential difference of 1 volt. So now let's just think about this. These charged particles, are accelerated to energies of more than 7,000 times 10 to the power of 9 electron volts. Alright, so I told you about the new particles and antiparticles, what they decay, and I told you about the accelerators. I'll have to leave here just to make sure that we keep this in time, in the time that we are allowed to. So that's me for now. Bye!